Alright, so we're looking at section 1.6 now. We're skipping a couple of sections there. You may want to look over them just to make sure they kind of look familiar, that you've seen stuff before. But the only thing that's going to be on the test are the sections that we actually cover. It's always good to know the other stuff though. And with section 1.6 we're going to talk about parent graphs and transformations. First thing you need to know is you need to know what the parent graphs are. And here are 3 of the 6 major parent graphs that you're going to need to know. And they are the constant function, the identity function, which is just the linear function, the absolute value function. Now you do need to know what these are here, what these properties are. Now these are the properties for the base graph, the parent graph. Transformations that you may do will change or can change these values for the domain and the range, and where it's increasing and decreasing, and et cetera, et cetera. So these are the properties for the base graphs, and you need to know what they are. You don't need to memorize them, but look at them and recognize them. And I'm not a big fan of the memorization. I'm a big fan of you knowing what it looks like and then being able to figure this stuff out from what you know it looks like. You should be able to look at this v and say, hey, it's decreasing from negative infinity to 0, and it's increasing from 0 to infinity. It's an even function because I can fold it across the y-axis and they're going to match up. So things like that. Take the things you already know and help them to use them to help you remember things that we're learning and we're talking about from here on out. All right, the other 4 that you need to worry about are the standard quadratic, a parabola, the square root function, the cubic function, or the x to the 3rd function, and the cube root function. Those you need to know as well. You need to be able to recognize and sketch those right off the bat. And then you're also going to be able to, by the time we get done with this section, you'll be able to know what little transformations of these things are going to look like as well, and you'll be able to change them. Once again, you do need to know the properties of these things, but more than anything, I want you to know what they look like and be able to identify this stuff from that. You can pause the video at any time along the way and copy this stuff down. I'm not going to slow down and sit here and make you stare at the video, but you can pause it and copy those down if you need to. Now, this table is in your book that you'll get whenever I'm able to give books out. And all we're doing here is we're talking about what the different transformations are. If you have y equals the function, whatever it may be, square root, x squared, whatever, and then plus c, it's going to raise the graph by c units. So same thing with minus c, it's going to lower the graph by c units, just changing the y values up and down. Horizontal shifts are going to occur inside the function. Notice here's the function. Instead of f of x, we now have f of x plus c. They're going to shift to the left if it's a plus c, and to the right if it's a minus c. Now you're probably thinking, well, wait a minute, to the right is positive and to the left is negative when we're talking about the coordinate plane. That's true. Inside we're actually changing and it's going in the opposite direction from the sign. Notice it's going in the normal direction for the sign with vertical shifts. Horizontal, things that are occurring inside the function, go the opposite way of the sign. If we have y equals the negative, or the opposite of f of x, all it's going to do is it's going to reflect the graph of f across the x-axis. So if it was a parabola opening up from the origin, if you throw a negative in front of it, it's going to flip it over and it's going to open down. Reflection across the y-axis is going to occur when you change the x value to a negative x. That's just going to reflect it across the y-axis. And then vertical stretching and shrinking are going to occur much the same way the vertical shifts and horizontal shifts do. If you're doing a vertical stretch, it's going to be multiplied outside the function, this little c right here, c times f of x. If c is greater than 1, it's going to be a vertical stretch, and the reason why is you're multiplying every previous y coordinate by c, but the x values are staying the same. So you're going to increase those y values for every given c. That's why it's a vertical stretch. If c is between 0 and 1, then you're actually going to shrink it. Where it was 1, if you're multiplying by 1/2, it'll now be 1/2. Where it was 1/2, it's now going to be 1/4. Where it was 1/4, it's now going to be 1/8, because you're multiplying by each one of those y values by 1/2, so it's making them smaller. That's where we get our vertical shrink. Now, with the horizontal stretching and shrinking, it's going to occur very much like the horizontal stuff up here. It's the opposite of the way that you would normally think. If you have f of c of x, f of c times x, you're going to have, if c is greater than 0, you're actually going to end up shrinking the graph horizontally. And if c is between 0 and 1, you're going to end up stretching the graph. Now, guys, you definitely know these top 4. These are not going to occur as much, but you need to recognize them, especially the vertical stretching. Horizontal stretching you'll see occasionally. Once again, if you need to copy these down or want to, you can pause the video and do so. Now, vertical shifts are going to occur when you add or subtract some value from the function. They are used with our parent graphs to sketch many of the graphs we're going to study. For instance, if we have this blue line right here, it's our base graph, and we're using x squared this time. But this can be any of the parent graphs. We're just using the x squared, y equals x squared for demonstration purposes. So vertical shifts are when we increase or decrease each one of the y values by the exact same amount. There should be an n in there. There are 3 equations graphed with vertical shifts. The first one we're going to look at is x squared minus 4. That's just going to take that graph and drop it down. And then the x squared minus 1, we're going to take that same graph, the blue graph, the base graph, and drop it down 1 unit. And then the x squared plus 2 is going to take that exact same base graph of x squared, and it's going to raise it up 2 units. So it's going to be there and opening up. So that's all the adding and subtracting after the fact does, is shift the thing up and down. Now, if we use the exact same base graph, y equals x squared, if we add or subtract a value inside of the function, then the resulting shift is sideways and opposite the way the sign would indicate. So here we have our base graph of the blue again, and the red is going to be the x squared plus 2 squared. So we've added the 2 inside the function of x squared, and plus 2 actually takes it and it shifts it to the left 2 units, not to the right. And x minus 1 quantity squared, and with the minus 1 we would think to go left, but it actually is going to go right. Any transformation that you do inside goes opposite the way you would think about it. All right, now if we have reflections across the y-axis, they're going to happen when the function goes from f of x to f of negative x. In other words, all the original function values that were positive now occur for x values that were negative, that are negative. Let's use the new base function this time. Now we're going to use y equals the square root of x. Now see, here's one of the things you need to understand. Remember, we can't take the square root of negative 4. It doesn't happen. We get imaginary. Imaginaries have no place on our graph. But what happens when we have the square root of negative x? Can we now let x equal negative 4? Well, if we plug that negative 4 in right here, negative 4 becomes the square root of positive 4, and that's going to be 2. That's why we have the point negative 4, positive 2 right here. So that's what that negative on the inside does. And here's what it does to the graph. It takes the base graph that was over here, that occurred only for positive values of x, and now makes it only occur for the negative values of x. Once again, if we put in, can we let x equals 4 go into this thing right here? Well, if we do, we end up with the square root of negative 4, and we can't find it. So that's why the red does not go over here in the positive x direction, and the blue does not go over in the negative x direction, because y equals the square root of x, we can only plug in these values over here that are positive. For y equals the square root of negative x, I can only plug in values that are negative so that the negative negatives cancel out to be positives, and I get real values. If I plug in a value over here, I end up taking the square root of a negative, which doesn't exist in our real coordinate plane. So when you throw in or change the x value that you're plugging in to a negative x, you're just going to reflect all the points across the y-axis. All right, now reflections across the x-axis. Well, think about this. If I go and I look at a given point, let's say we're talking about this point right here, and then I go and I look at this point right here. Well, did the x value change at all? No. But what do we notice about the y value? The y value is roughly about the same value, isn't it? But down here it's negative and up there it's positive. So that's all we're doing, is we're changing the y values to negative. Well, remember, what is f of x? F of x is nothing more than y. So every value that we had before the base graph of the square root of x, we're now making negative by throwing that negative out in front. That's where we have this reflection that goes from there down to there. So the blue graph, once again, is our base graph. The red is the reflection of negative square root of x, where all it did was it changed every single y value's sign from positive on the blue graph to negative on the red graph. All right, vertical stretches or shrinks are going to occur when you multiply by some number. A stretch is going to occur if a is larger than 1, and a shrink is going to occur if a is between 0 and 1. Now, we don't talk about values that are negative because we've already dealt with those with our reflections. So if we have f of x becoming a times f of x, if a is larger than 1, it's a vertical stretch. If a is between 0 and 1, it's a shrink. So the blue, once again, is the absolute value of x. So here's our base graph right here. And if we multiply that base graph by 2, or that equation by 2, notice here the y values are going to grow twice as fast. Where I had 2 here, 2 there, so I had the point 2, 2. I now have the point 2, 4 on the red graph, because my y values are going to be double what they were originally for any given value of x. Same thing when I get to 3. Where it was 3, it's now going to be up here at 6. It's going to double. Now, what happens when we multiply by 1/2? Well, the same thing happens. It just happens in the opposite direction. Where we did have 2, 2 before, well, what's 1/2 of 2? It's 1. So we have 2, 1. Where we had 3, 3, we now have 1, or 3, 1.5. 4, 2. So what happens to every one of my y values? They are half the value that they were originally with my blue. Now, a horizontal stretch happens similar to the way a vertical shift works. We have y equals the square root of x here, and the red is going to be multiplying the x inside the radical by 2. And notice here, what's going to happen is it's going to take less time to get up to a certain value of y. Because think about it this way. Let's think about a certain value. Let's think about 4. So when we get to the square root of 4, x is equal to 4, right? and that's going to give us a value of 2. Well, where am I going to end up getting the square root of 4 here? I'm going to get it when x equals 2. So now where I did have 4, 2 right here, now I have 2, 2 with the red graph. Notice they're at the same level there. So what do I notice? The y values are growing faster when I have a number in here that's bigger. So what it looks like is it shrinks horizontally. Now what about with the 1/2? Well, how am I going to get the square root of 4? What does x have to be to give me the square root of 4 in this thing? Well, x would have to be 8. 1/2 of 8 gives me 4. And if you look here, if we go all the way out here to 8 and go up to 2, guess what? Boom, it's right there. Same exact value. Same exact y value, but where it did occur at 4, when we multiply by 2 inside, it's going to occur when x is 2. We multiply by 1/2 inside, it's going to occur where x is 8. So that's where you get your vertical stretch or your shrink. All right, that's it. We'll look at some examples of those when we get into class.